Today's lecture is going to go over the significance of sunlight. We're going to be focusing our time and energies on the electromagnetic spectrum. So let's get something straight. A photon leaving the sun is going to travel 93 million miles or 150 million kilometers through the vacuum of space to reach Earth. So that's what this picture here is showing. And we're simply looking at the directness of sunlight is going to influence the amount of heat energy or the heat density. The greater the heat density, the warmer the conditions. And that's what we're looking at here. So we're going to study this in terms of the electromagnetic spectrum. So let's look at the electromagnetic spectrum. So above, this is what this picture is here. We have from gamma rays, from very high frequency, very short wavelengths, through X-rays to ultraviolet or UV, to visible light, infrared, microwaves, and long radio waves. When we compare a gamma ray to a long radio wave, they have different frequencies and they have different wavelengths. Well, let's talk about sunlight. Sunlight is pure energy released from the thermonuclear fusion from our local star that we call the sun. Of the wide range of energies released during the fusion process, we typically pay most attention to the visible light spectrum. Visible light consists of white light, and if separated with a prism, we find that white light is comprised or composed of Roy G. Biv, or red, orange, yellow, green, blue, and violet. These colors, the Roy G. Biv, cannot be separated into anything further. The sunlight leaving the sun, traveling to Earth, travels 93 million miles, or 9.3 times 10 to the 7 miles, all of which at the speed of light, 186,282 miles per second. Nothing travels faster than the speed of light, or what we'll call letter C. All of these are forms of pure energy: gamma rays, X-rays, ultraviolet, visible light, infrared, micro, and radio waves. They're all pure energy. They're all a part of the electromagnetic spectrum. So let's apply this to the greenhouse effect. The greenhouse effect is the natural process of Earth's reception of sunlight and the corresponding heating of our atmosphere. Here we see incoming sunlight that reaches our atmosphere, and a few things can happen. Some of the light gets reflected, right? It simply bounces off. Some of it gets scattered, which is a form of reflection. It just bounces off in different directions. Some of it gets absorbed. We'll be looking at the process or the feature called albedo. Different colors, light and dark, are going to influence what gets absorbed. And some of it gets transmitted, continues to be transmitted through the atmosphere, simply passes through. So let's look at what light and energy are. Well, let's see. Light is simply pure energy. Visible light that enters our atmosphere has a shorter wavelength. Look here, visible light has a shorter wavelength than the heat energy or infrared energy that is re-radiated back into space. Heat energy or infrared is considered to be long wave energy, longer waves than the original visible light. In other words, infrared is on the longer wavelength side, so sometimes it's simply referred to as long wave radiation. So let's look at this slide. Let's make sense of shortwave as visible and long wave as infrared or heat. We have the incoming shortwave radiation. It gets absorbed by different materials. The net that gets absorbed of the shortwave radiation is larger. So there's an increased outgoing long wave radiation, right? Well, where you have light that's going to have a high reflectance or high albedo, we're going to have incoming radiation. The net that's absorbed is going to be smaller. So there is a decrease of outgoing long wave radiation. Okay, so let's go back and consider sunlight. It's a form of pure energy. So the sun releases many forms of energy, right? Visible light, ultraviolet, infrared, and X-ray. These are all emitted from the sun, and it travels in the form of photons from the sun to the Earth through 93 million miles of space, through the vacuum of space, and reaches the Earth's atmosphere. The greater the angle in which it reaches the Earth's atmosphere, the greater the heat density. Therefore, the warmer the conditions of that area, which we're going to measure in watts per meter squared. Notice, if it has an angle to it, that area of light is going to be spread out. It's going to have a lower heat density. So let's go back and make sense of the electromagnetic spectrum one more time. All parts of the electromagnetic spectrum are pure energy. They just vary in how much energy by their frequency. The greater the frequency, the greater the energy. Gamma rays are the highest energy. They have the highest frequency and the smallest wavelength. Radio waves have the lowest energy, right, based on the low frequency and the largest wavelength. These are all based within the electromagnetic spectrum. Notice red and blue colors. Well, technically violet. But red has the largest wavelength. It has the lowest or least amount of energy, whereas the blue and the violet end have the highest frequency and thus the highest energy. All of these energies travel at c, the speed of light, 186,282 miles per second as they travel through the vacuum of space. Wave speed is equal to frequency times wavelength, or c equals frequency times lambda. So all of the energies travel at c, but they vary in their frequencies and their wavelengths. So let's put this all together with the greenhouse effect. So the greenhouse effect is the result of radiant energy that is generated from the nuclear fusion that takes place in the core of stars like our sun. Sunlight, or visible light, has a shorter wavelength than infrared. So therefore this energy that enters our atmosphere gets absorbed by different materials. The materials re-emit the energy as heat, or infrared, generally called long-wave radiation. Visible sunlight is pure energy and a part of the electromagnetic spectrum. It contains energy. So notice what happens. Some of the light gets reflected, some gets scattered, some of it gets absorbed, and then our atmosphere heats and traps that very long-wave radiation because of greenhouse gases. Now, it's a common and normal experience. It's not a bad thing. The question is, are human processes affecting the atmosphere that's increasing carbon dioxide and other greenhouse gases, including methane? Are they altering the amount of heat in the total heat budget that is not allowing some of that heat to escape into space? That's the question we're looking at. So last but never least, if we take a look at the total amount of solar radiation, we can start looking at percentages of what's happening here. Roughly 30% of the total sunlight that enters Earth's atmosphere is reflected directly back into space. Of the remaining 70%, 20% of that radiation is absorbed by our atmosphere and clouds, and 50% is actually absorbed by land and sea and then re-radiated back into space. A key to this to recall is that our troposphere is heated from the ground up, based on the different material that is covered on the ground. But we can define this as simply albedo. Different materials are going to absorb and reflect heat a little bit differently. So now let's apply this to aerosols, little tiny particulates, such as dust, ash, sea salt, pollen, and microorganisms that are airborne suspensions in our atmosphere. These aerosols can actually absorb, reflect, and scatter sunlight back into space, thus decreasing the amount of sunlight energy that reaches Earth's surface. For example, the Earth can have a short and temporary cooling period immediately after a volcanic eruption. For about 1 to 3 years, it takes time to recover or stabilize our atmosphere. As the ash travels around the Earth, it reflects sunlight back into space. Eventually, the volcanic ash settles out of the atmosphere and climate recovers to normal conditions as to prior to that atmosphere or that volcanic eruption. So all in all, we're looking at what is taking place with this sunlight. We're looking at visible light, we're looking at long-wave radiation as infrared, and we're trying to make sense of it as to how it applies to the greenhouse effect.